you have any questions along the way, let us know.
Sounds good. Great.
Okay, cool. So we are the CUSail, we're the Cornell's autonomous sailboat team. We're a project team and we've been around for, I guess, a couple of years now. My name is Alexandra, I'm the full team lead of CUSail.
I'm Rafi, I'm the mechanical team lead.
I'm Ryan, I'm the navigation team lead.
I'm CJ, I'm the business operations team lead.
So to tell you a little bit more about our team, we have around 35 members, around 8 majors, and in 3 different colleges in Cornell. We have 3 sub-teams. We have the mechanical sub-team, which takes care of the boat's infrastructure, as well as all the hardcore engineering building stuff. We have the navigation, which takes care of our software and hardware algorithms, as well as our business team, which takes care of mostly making sure team stays afloat, I guess all the logistical operations, as well as getting in contact with team school about budgeting and whatnot. So our team initially started out as a research project in which we tried to figure out how can we make a sailboat autonomous and how can we make it most mass producible so that it's easy to do oceanic research. And from there we kind of evolved into a team that now builds a boat to use the competitions. And however, despite the fact that we're still doing competitions, our end goal will always be to do oceanic research. So that's where we currently are right now, and yeah. So how we work, we have usually a couple of sub-team meetings per week, usually to kind of get together and make sure that everything's built properly. And then we usually test our boat on Cayuga Lake, which is here. Usually do it at the sailing center, usually have a blast out of it. We take a day and, I don't know, just enjoy some pizza and see if our boat works. And then we also test on the engineering quad. So whenever we don't get a chance to kind of take the whole team down to the lake, we kind of take the boat onto our shoulders and just parade her around the engineering quad, hoping to see if our algorithms and our sail turns the way it should.
So currently this is our boat. It's called the Codfather, and we built most of it last year. We use an airfoil sail, which is kind of like an airplane wing. I'll talk about that more in a little bit. And yeah, that's the mechanical side.
Yeah, in terms of the navigation side, we have both remote control and autonomous capabilities, meaning that if we need to, we could take over and kind of input the angles into the sail and to the rudder directly. Besides that, when it is functional, we do have long-range control up to 1 mile. That's kind of what we've been working on recently, our transceiver and radio. And then besides that, in terms of sensors we're using as inputs into the boat, we have an anemometer, which takes in wind direction. We have an IMU, which is kind of like our compass heading. And we have a GPS, and we're currently also working on computer vision, that being the camera going into the boat. So when that's working, we'll ideally be able to detect things like buoys in the water and avoid them.
So what competition do we go to? Our competition is called Sailbot, and it's International Autonomous Sailboat Competition. So we usually have 5 events during the competition. We have the navigation test. So they give us basically buoys, and we have the coordinates, the GPS locations of those buoys, and they start our boat off at some random location, and we have to precisely navigate to those buoys. And then this is without remote control. This is all kind of we press start, and then the boat sails by itself.
Is it fully autonomous when you're in that boat?
Yes, in theory it is. We still have to perfect that, but that's the idea of it.
I'm sure there's a lot of testing.
Absolutely.
Yes, indeed. Next up, we have the fleet race. This one is mostly RC and autonomous control. It's at the very beginning of the competition, kind of does your boat work? Can it be RC'd in worst case scenario? And then we just basically have a fleet race. All the boats go on the water, we have a race, see who's first. Next up, we have long distance race, which is, we have, 2 buoys about half a mile apart. And from there, we kind of see who can stay on and who can do the most amount of loops around those 2 buoys. And that's long distance. Station keeping is buoys are set up into a square, and the goal of this event is to stay inside of the square as long as you can. And then, maybe not as long as you can, for around 2 minutes. And then after that 2-minute mark, you have to promptly leave the square within 30 seconds. And then finally, we have presentations. So basically what we're doing right now is kind of get you inside about what our boat is, how we built it, and all the fun electronic stuff. So over the summer, we got 4th place overall. We got first place in precision navigation, and we got second place in endurance.
Cool, so now I'm gonna give you like a little mechanical overview of the boat. So this is kind of the main structure of the boat. So we have our sail, the hull, our rudder, and our keel, which has like a bulb of ballast on the end, stability. We took for the hull, which in the next slide. So, okay, this is the sails first. So the sail, I assume most of you sail. So so typical sails are made out of cloth, and you can like kind of pull them in and let them out using a rope. However, for an autonomous boat that doesn't use a person, it's kind of hard to get all the ropes to be at and the sail to be at the angle that you want. And so we made a rigid airfoil sail, which is essentially like an airplane wing, just rotated 90 degrees. And that kind of creates the specific amount of like force on the sail that we want, and it kind of allows us to be a little bit more exact with how we sail. And we basically connect, so the sail is connected to this carbon fiber tube, which is then put into the boat and connected there, and we can rotate the sail at whichever degrees that we want inside the boat. So it also helps, because our boat is very close to the water, if there's any splashing and stuff, there's really nothing that's outside the boat that can be damaged by water. And here you can see kind of what's inside the sail. The skeleton is made out of like thin balsa wood that we laser cut, and then we wrap it with a material called monocoat, which is this like plastic kind of thing. And yeah, our hull, we built it last year. It was made using, so this is kind of our drawing in CAD. And we have about 6 ribs on the boat, and we put like, it's basically a wooden construction. So next slide is the manufacturing of it. So we cut out these ribs, screwed them onto a board. They're made of, in order to cut them, we used kind of 4 basically sheets, basically sheets of wood, and we cut them out and we glued them together. So here you can see kind of one of our ribs. There's 4, and we just like glued them together, and then we put them on a wooden kind of plank and screwed them in, and then we used that to kind of lay out all these longer pieces of wood that we then screwed onto each of the ribs. Here is, so as you can see here, we need to bend the wood. And so what we did was we steamed it. So here's our kind of makeshift steam bag that we made. And we just put these long pieces of wood in this bag and steamed them for about 20 minutes and allowed them to be very loose, and we could make it into whatever shape we needed.
Is this model making plywood?
Yeah, we used Baltic birch plywood. It's like the longer pieces are 1/8 of an inch, so they're really thin. We weren't sure how we were going to cut them when we got them, but we were able to just use like an X-Acto knife. They're really thin, really easy to cut out. So for like these pieces, we was unsure when we were making it kind of how we were going to get them to all kind of go down to this end, and we just had to put them on and cut them in the way that we needed to, and it was really easy to shape them out. Here, the next slide you can see is our more final version. So this on this picture you can see kind of how all the pieces connected, and then there were some gaps in them, and we just took all the like wood shavings that we had and mixed them with wood glue and like put them all to patch up all the holes. And once we were done, so here you can see when we unscrewed it from the plank, this is our hole, and you'll be able to see more inside when we show you the actual boat. But so we flipped it over, and then we put a layer of carbon fiber on top of it to give it some strength and just to waterproof it and kind of to protect all the holes and make it smooth. And yeah, so our inside the boat this is how we rotate our sail. So we have a servo here, which is connected to our mast, which then, so the mast comes into the boat here, and just we pin it into this tube, this like connection point, and we can just rotate the sail. Now our keel it's a flat plate keel, pretty long, and it goes down and it connects through this connection, and we just bolt them in here, and then we have our ballast at the bottom. It's about 6 pounds, and just to add stability for the boat so it doesn't tip over. And our rudder, it is it's made out of Alaskan cedar. Here you can see how it's connected into the boat, and this allows us to so the servos then connect to these linkages, which is connected to the rudder, which goes down into the boat and outside. And we made them using it's called CNCing, which is computer numerical control. And essentially you just have like a block of wood, and you put it into machine, and you give it like a 3D drawing, and it's able to like cut out that drawing in order to make them. And yeah, here's the physical part, and I was kind of just shaving off all the pieces so that we can fit in our metal post so that it can connect to the boat. And yeah, that's
All right, so onto the navigation side.
yeah.
We can skip that. This is kind of just a systemic schematic of how our boat functions. We have a battery feeding into our battery management system, which essentially powers everything on here. We have a transceiver, which then gets fed into a Raspberry Pi along with our compass heading, our GPS, and our anemometer, which is fed into an ADC so the signal is filtered properly. A Raspberry Pi is essentially the brains of our boat. It's like a computer, essentially. Skip that. So yeah, this is just kind of a picture of how that ends up looking. We don't make this ourselves. We do design a circuit board that kind of goes on top of that. So we created something which is called a Raspberry Pi shield. It's kind of like, if this is the brain of our boat, then that would kind of be like a spine. It's where all of the inputs and outputs connect through so the Raspberry Pi can access them. In terms of control, we have an anemometer. That's a picture of our wind vane. Right now, we aren't currently using it to measure speed, only direction. And then this is a picture of our ADC as well. This is our GPS, also pretty self-explanatory. During competition, they'll feed us coordinates actually for some of the events we participate in, and those essentially function as buoy locations on the lake. This again is called an IMU, which stands for Inertial Measurement Unit. Functionally speaking on the boat, we're really only using it for compass heading, just to make sure that we're keeping everything standard with the directionality of the boat. And this is just a screenshot of the software we'll actually use to calibrate it correctly. And then, of course, our transceiver, our XB radio, it has been giving us some trouble in the past, so it's kind of what we're working on right now. When this is working, we should have up to 1 mile of range to communicate wirelessly with the boat to and from. And this also would enable our consistent remote control of the boat. This is a graphical user interface that we can actually use to interface with the boat when it's working. Essentially, it'll feed in our wind angle and other things like that coming from the IMU and anemometer. And it kind of acts as an embedded interface for everything functioning on the boat, so we can tell in real time what's happening and what needs to be done.
Yeah, just to add a little bit, these orange dots are like the buoy locations that you can see, and then all these plus signs are the waypoints that we get to, and the redder that they are is the closest to, basically the red to the blue, it's a kind of a color distribution of like which waypoint you're going to first. So all the ones that are closer to blue is the last waypoint that you're getting, and the closer to red is the first one that you're going to.
And then this is also something we're currently working on. This is a Raspberry Pi camera. Essentially what this would allow us to do is look at what's ever at the front of the boat, and then via an algorithm which we're working on, detect whether or not there's a buoy or some sort of object we should avoid that's in the water in front of the boat. And then again, our servo motors, and we have a PWM going into that as well. In the past we had some issues related to the Raspberry Pi where it was jittery. So we installed this to basically feed from the Pi into the servo to avoid that jitteriness. Because essentially what PWM is, you're sending a very tightly packed digital signal to simulate an analog signal, if you can't, coming out of the computer. And the way the computer kind of organizes its data, if it's trying to do too many things at once, it can kind of make it jittery because you end up only sampling certain points from that curve. And this is our current battery. It's a lithium polymer battery, 12 volts, and then that eventually gets fed into the Pi at around 5 amps, I believe. Then we can go to the algorithm. Skip that. Yeah, so this is just another kind of systemic block diagram of how the boat works. We have our input systems, our wind direction, our compass, and our GPS, etc. that get fed into the algorithm. This is kind of where decisions are made on the boat. Autonomy is all about setting decision making beforehand. So you have certain inputs, you want to make decisions consistently based off of those inputs. So our inputs, again, to reiterate, being where we want to go in the water, where the boat currently is, where the boat's faced, and the absolute wind direction. So not just relative wind direction to the boat. And then again, our output from the algorithm should be the current direction to sail, which then gets fed into our servos. And then the goal, of course, is to maximize our speed going towards that object. So, of course, I'm sure you guys know sailing and whatnot. There are trade-offs between beating and staying course. I don't have previous experience sailing, so I'm going to try my best to explain this in a way that would be palatable. Basically, what you're trying to do is execute beating maneuvers, and that takes time and energy. And you want to avoid veering too far away from the target. I'm not sure if you want to pitch in a little more to that.
Yeah. So kind of it's all a trade-off between determining how many times we need to tack, how many times we want to tack, because as you were saying, it's a trade-off between how much energy we want to use and how far away we want to be from the point. Because if we're going if we don't like adjust where we're going, we might drift too far from the path. And if we turn too much, we can be a lot slower than we want to be. And so that's basically kind of the algorithm. Well, a big thing about the algorithm is like how much should we be turning and adjusting the sail.
Which I believe should be on the next slide.
Yes.
Maybe the next one. So yeah, this is kind of just explaining, we have a left side optimum and a right side optimum. What this essentially is one direction is always going to be the global ideal direction. That's if the boat was completely controllable, we didn't have to worry about wind or water, we would just send it directly towards that buoy. But in reality, of course, we can't do that, we're a sailboat, so we have to settle for something a little more practical. And then this is what I was kind of talking about earlier with our tacking. The way the algorithm's set up right now to avoid the specific math that goes into that is as we get closer to the target, we tack at a higher and higher frequency. So as we're further away, we have a little more of an amplitude, and as we get closer, we kind of veer in. I'm not sure if I'm going to take this one as well.
Yeah, so this is kind of velocity. This is VNG's velocity good, which in our previous slide is essentially just like how fast are we going to the target. So it's not necessarily like, it's not how fast the boat is moving, it's how fast we are moving in the direction that we want to be turning. So the algorithm's all, it's kind of a struggle between how it's maximizing our velocity made good. And so this is a polar diagram to help kind of understand what that is.
And then of course we want to know when to tack, going off what I was previously saying. So to find the best heading for the boat, do you want to take this one as well?
Yeah, so N is our hysteresis factor, So it's kind of, you can read it by what factor does the global optimum have to exceed the local optimum. So basically, if it just determines this equation kind of determines whether we want to turn or not. So velocity made good is, that's like kind of our current path, and is our new path, our new turning, is that going to be better than our previous velocity made good? So that kind of determines. So every time we check for when to turn, we determine if we turn, is our velocity going to be faster than if we can maintain our course?
Yeah, because all autonomy essentially is translating decision making into mathematics that we can implement on a computer. So this is a really good example of that. If this value is greater than that, then we'll switch based off of our inputs. Right now, I think that's actually old. We execute the algorithm at 1/4 hertz, meaning every 4 seconds we'll actually change the angles of the servos. And when we are kind of iterating through all the targets, that kind of gets changed continuously over time as we're going through them.
Yeah, so we kind of do this, the previous equation that we're doing, we do that every 1/4 second. And so
Or every 4 seconds.
Every
Quarter-
4
quarter
seconds,
hertz.
yeah, my
Input,
bad,
yeah,
my
yeah.
bad. Every
You're
4
good.
seconds, we determine that.
Yeah, and then this is kind of some pictures of testing we've done in the past. Occasionally in the workshop, we'll set up a test bench if we don't actually want to put stuff into the boat. We just want to test inputs and outputs to make sure everything's working on the electrical side. I'm not sure if you can tell, I'm more of an ECE, I'm more of an electrical engineer, I'm not as familiar with the mathematics. Then this is a picture of us working on Cayuga Lake. We have a canoe over there as well near the sailing center that we'll take out to retrieve the boat when it fails. And then this is us testing on the engineering quad. Like she was saying before, we'll actually put the boat on our shoulders and just kind of angle it different directions and see how the sail and rudder react to certain wind directions. And then during our stay at competition, we actually did some testing in our Airbnb as well, last minute.
Yeah, thanks for listening. You guys have any questions?
Yeah, how did you build this?
How do you keep your VMD?
Well, actually, it's very close to that. How have you input your sail trim? Do you have a fixed pattern that you've already programmed into the software, I guess, that says the precise angle of attack for your wing sail?
Yeah, so we have, so our airfoil is it's called a NACA 12, I don't know if anybody knows what I'm talking about, but it's essentially just, that determines the geometry of the sail, of the shape of the sail, and that has an optimal angle of attack of, I believe, like around 7 to 9 degrees. So if the wind is coming from this direction, this is if our angle of attack is 0, so we put it at like around 90 degrees, which is essentially 0, but it's a little bit enough to be able to create a force that will push us in the direction that we want to go. And in our algorithm, we have a whole section that determines if the sail is if the wind is coming from this direction, we put our sail at this angle, and it is yes. I think that answers your question.
Yeah. So you've fixed the patterns, or the settings, so to speak, already in the software.
Yeah. Yes. Yeah.
Okay.
And our new algorithm now, right? That's now not true, I believe.
I'm not sure, I haven't delved into the math. A former member of ours, she's doing a PhD at Illinois right now, and she was so kind as to basically write a neural network in a simulator for our boat. So what that essentially does is, once we get a good enough computer with our budget, is we're able to run the simulator on that computer and then basically use that to train our boat overnight at a really fast rate.
So currently, we basically just say we take in the wind angle, and we, from that direction, we determine what is the optimal angle of our sail, which is determined by kind of a section in our code. And we've I believe from the team that whoever wrote the algorithm, we have a research paper that we have been using, which we quoted in a bunch of the presentation, and that kind of talks about rigid airfoil sails and what is like the optimal angle for sails, for our sail. Because the biggest difference between our boat and like a regular sailboat is that a regular cloth sail, the wind you can catch the wind, so the wind kind of pushes the sail because it can like hold all that wind because it's kind of at this curve. But ours can't catch that wind, so it can only create kind of lift in one direction, whereas the sail can kind of push more forward. So our keel is really helpful because it helps to create a force in the other direction, which helps us kind of the two forces going kind of in opposite directions, but also both forward, kind of help us to go forward. That makes sense.
Can you go to that slide where you showed 3 paths and moving? Previous
This
one. After this one. Yeah, this one.
Yeah.
There's P1, P2, and P3, right?
Yeah.
So when you code it, the optimal would be P2 in your case, right now?
Yes.
Okay.
Remember,
Yeah.
John.
I can't get Rajiv to sing.
We're the racers back
Because P1 in this case uses too much energy, and kind of our goal is, because we don't have a person in the boat, we want to use as little battery as possible.
Yeah, and that goes back to our frequency of change. The reason is that every 4 seconds is purely because of battery life. If we raise it any more, then we risk running out of battery, especially for the endurance of where ideally we stay on the water for like 7 hours during the day if that's up and running. But going back to this, if you go to the next slide, I believe, the one where it's variable, or it's the one with the map. This one. So usually it'll be around P2, but it's variable as well. So the further you are away, the closer you are to something like P3, where you're not making as many adjustments, but as you veer in, you increase your specificity essentially.
That's pretty much what we do when we're racing.
Which, anyone who's raced here, it's 50% skill and 50% luck.
It's like,
So how many?
Especially here.
How many of you are sailors?
Well, the two of us.
Two of us are.
No?
No, I mean in the group.
In the
total.
group, it's honestly it's very little. Surprisingly, it's very little for the size of our group.
Yeah, maybe at most 5 of us out of 38. So we definitely benefit from some sailing lessons.
We're gonna poach them all as crew. They're all.
Lauren's
They're gonna
gone tomorrow,
join.
so
Yeah.
I lost my job.
They will be joining the cruising fleet.
Here, if you have more questions, I was talking about that research paper. I believe this one is the paper. It's called Autonomous Sailboat Navigation for Short Course Racing.
Well, it would be interesting because we have our fixed marks with GPS coordinates. When we go outside, we can see, we have them half a mile north, south, and a mile north and south. So you actually have a test course
That's
available
good
to
to
you.
know.
And there's 1 mile across the lake too.
Sounds good.
I did. Oh,
Oh,
go ahead.
do you do anything, like, are you guys familiar with roll tacking at all? Or like, do
Yeah.
you do anything with like, I don't know if this is like with your boat or other boats, like any shifting of ballast or keeping the, if heel was a factor at all with any of your?
We try not to,
Okay.
because we're concerned with kind of all the components that are in the boat, and if we get water in there, it's not great. Our battery can just like go up in flames.
Yeah.
So we really try not to, and especially we want to move into doing more research
Mhm.
stuff. And that involves a lot more stability, and so we want to try and have as little healing as possible.
How much do the designs vary? You know, when you go to a competition, do all the boats look similar to yours? Or
Yeah.
do you have a picture of?
I think we do.
Yeah.
If like one of you did.
Yeah, there's quite a big difference, especially last year. A lot of teams had 2 rudders. So when they're
It's
kind
a
of
trendy thing these days.
yeah.
So this is our full team meeting slides.
And another boat had a really interesting design.
Was that WPI?
Yeah, WPI. Okay, so this boat also has 2 rudders here, and this one had as well. Their sail was, I don't know, I think about 6 feet tall compared, and their boat was only about this big. It was a very large sail compared to the size of their boat. And this was WPI. This is the team that won. What was interesting about their sail was they didn't control the angle of the sail. They have this, what was called like a tail sail, which is in the back. And so their main sail kind of went into the direction of the wind. and then this tail sail in the back, they only rotated that one, and that one helped to create, based on the direction of the wind, it helped to create kind of a little bit of a lift that would help them push in the direction that they needed to.
They also had a very wide hull as well, I remember.
Yes, yeah.
Good. They used to have trim tabs on boats on the back of the keel.
Mhm.
Similar. Great. I have a question about the radio. You were saying that, I'm not familiar with Yaxbee, but what type of, you said you have problems with distance with it?
Yeah, currently. At competition, we had thought it was more of a current thing, but in reality, it's just probably quality of product. So we're currently working on replacing it.
Okay, because I was gonna say, if that's in the boat, when you don't have an antenna, you know, at a mile, you start to get the curvature of the earth
Yeah.
effect, so.
Yeah, we're working on that right now. We have an antenna ordered as well. A lot of our electrical projects this semester are RF related.
Any other questions?
No, you can't put one on your boat.
I want some software.
That breaks your one design rating. Oh, you can put one on your boat. Yeah. The ratings committee will take that into consideration.
So broadly, you mentioned that, you know, all of this work is basically designed to think about and do oceanic research. So, I wonder, you know, do you imagine these boats to basically be out there in the ocean by themselves, recording stuff as a way to basically, you know, what is the final imagination of
Yeah.
what these boats will achieve for us in a way?
So currently there is a company already that does autonomous sailboats about our size and scale that is very much an ocean research boat, and then it goes into the ocean. It collects solar powered and salinity, temperature of the ocean. Some even have echo sensors to determine the bottom of the ocean, and it's like how geographically it looks like. So some sensors like those that like a company already has. So for us, we would try to implement mostly the same things.
Okay.
So start off there, see what's already done, and kind of like, okay, how can we incorporate like a thermometer? How can we incorporate salinity? How can we use solar panels to make sure that like our boat can last longer?
Right.
So those are some of the considerations that we were trying to, at least on the first step, implement. And then once we get more proficient in like those instruments and understanding how they work, maybe we can incorporate like an echo sensor or perhaps even pH content. So.
Yeah, I remember we have a student who's working kind of to figure out what we want to research, and they spoke to an oceanic professor, and they had mentioned that figuring out like pH levels on lakes and oceans is like a very important thing. There hasn't been much research on it, so.
And then to put that into a little bit more perspective, like all of that can help determine, for example, like pollution of a lake or for Krieger Lake, or perhaps determining like how much the water levels rise and fall each year. So, okay.
Alright, should we go to part two?
Yeah, let's go to
Alright.
part two.
Sounds good.
See if there's any wind.
Thank
See
you.
if the trees moving.